Hello, everyone. My name is Jicheng Liu. I am a master's student at Northwestern Polytechnical University. Our work, 3D Geometry-Aware Deformable Gaussian Splatting for Dynamic View Synthesis, has been accepted by CVPR 2024. Dynamic view synthesis aims at rendering novel photorealistic views at arbitrary viewpoints, and any input time step given a monocular or multi-camera video of a dynamic scene, which has broad applications in virtual reality and augmented reality. Due to the inherent motion ambiguity in monocular dynamic 3D representation, dynamic scene modeling and synthesis are more challenging. One common strategy is to represent the dynamic scenes as a combination of a static canonical field and a deformation model. Recently, different deformation models have utilized the local geometric information, originally in dNRF. The feature of each sampled point is extracted independently with each other. Following works notice that this method could not handle the complex dynamic scene, since the extracted features contain little information from neighboring points. Then interpolation is introduced to fuse features of neighboring grids. TinyVox and SUDS interpolate with multi-scales. Nevertheless, the interpolation operation is rather simple in extracting local geometric information and introduces unsmoothness in artifacts. Building upon the recent explicit point cloud-based Gaussian splatting representation, we introduce a sparse CNN to extract 3D geometry-aware features. Compared with simple feature interpolation, the CNN is superior in extracting local information and has a much larger reception field. To model dynamic scene, we use a neural network to learn deformation of position, rotation and scaling of each Gaussian. Because rotation is in SO3, neural networks exhibit greater proficiency in learning a continuous function, as opposed to a piecewise function with discontinuities. We use a continuous 6D representation proposed by Joe to model rotation. We also modify the density control since it comes from the current timestamp demand at the moment. Our method mainly consists of two core components. The Gaussian canonical field is used to learn the reconstruction of static scenes, while the deformation field is used to learn object deformation. The geometry-aware features consists of two branch. Geometric branch leverage the sparse CNN on the sparse voxels to extract local geometric feature. To avoid points in the same voxel having the same features, we add identity branch, which gives each point a unique feature of itself. Finally, two branch features are combined via a simple MLP. We adopt an MLP as the decoder, which takes the geometry feature, the position of each Gaussian, and timestamp as input, outputs the deformation of each Gaussian from canonical space to time t. Then we transform the Gaussians from canonical space to current time space according to the outputs. Once transformed, a standard rasterizer is used to render photorealistic image at current time and specific location. We conduct experiments on both synthetic and real datasets to verify the performance of our method. The experimental results show that our method could recover correct geometry for canonical time, which proves that ours learns accurate deformation field. Meanwhile, we visualize the geometry-aware features. Results show that our model has correctly learned the geometry and dynamic-static relationship of the scene. We compare the experimental results of SOTA method. The qualitative results show that our method performs better, especially in detail areas. In contrast, other methods have shown varying degrees of artifacts. Compared with synthetic datasets, real datasets are more challenging due to the narrow camera viewing range and pose ambiguity. Can be observed that our method also achieves good performance in them. In addition, we also provide visualization results of the Gaussian's trajectory varying time. It is shown that our method has learned correct point tracking, which means that the model learns better deformation. It's all. Thanks for watching.